Welcome to Engineering Mechanics Statics, Chapter 9. This is the last chapter. This is Moments of Inertia. In this chapter, we're going to not cover the entire chapter. We're going to kind of do a high level cover of a few of the topics of this chapter. So let's do a little introduction. Previously, we've considered distributed forces, this is Chapter 5 stuff, right? Which were proportional to the area or the volume over which they act. So to find the resultant of that, you summed or integrated it over the areas or the volumes. And the moment of the moment of the resultant about any axis was determined by computing the first moments of the areas. Okay, we're now going to consider forces which are proportional to the area which they act, but also vary linearly with distance from a given axis. Okay, so we're going to show that the magnitude of the resultant depends on the first moment, just like before. But the point of application of the resultant depends on the second moment of the distribution with respect to the axis. So this chapter we're going to talk about some methods for computing the moments and products of inertia for areas and masses, both areas and masses. Okay, so let's try to be a little more specific. I know it's a little bit of a not super clear at this point. So let's show you an example of what we're talking about. So if you consider distributed forces, some delta F, right, whose magnitudes are proportional to the elemental areas delta A on which they act. So in other words, look at this. So this amount of force is proportional to how much area. So if you double the area, you're going to increase the force. If you make the area smaller, you're going to decrease the force, right? So that's what it means. It's proportional to the area in which it acts. But in this case, it is also going to vary with the distance from a given axis. The further you get away from this x-axis, the greater your force is. So, for example, consider a beam. So you have this beam, right? And it's subject to pure bending. You're just trying to twist it. Okay, so the internal forces, the forces inside the beam, are going to vary linearly with distance from the neutral axis, which passes through the centroid. So what does that mean? This thing's trying to bend around this axis. So right here, you're not going to have anything going on, right? Down here, this is going to be under tension. You're going to be pulling it away from each other. The further you go down, the more tension's under, the larger the force is. You go up in this direction, it's going to be under compression. You're squishing it, right? And so as you go up further and further, you're getting under more forces. And so not only is the force proportional to the how much area it's acting on, but it's also proportional to how far away it is from a given axis. That's what this is saying. So delta F is ky delta A, right? And so the resultant is going to be, you're going to integrate that up over this area and you're going to have the first moment. However, the moment, you're going to have the force times the distance from the axis, right? So this is the force right here. And then you multiply it by another y for the distance, because moments of force times distance. And you end up with the integral of y squared dA. And this is what we're going to call the second moment. Okay, so the moment of inertia of an area. Okay, second moments are moments of inertia of an area with respect to an axis. That's what we're going to call them, the moments of inertia with respect to an axis. Now, again, it's important. It only makes sense to talk about the moments of inertia if you are talking about with respect to some axis. It's only with respect to an axis. Okay, so the moment of inertia with respect to the x-axis, ix, is integral of y squared dA. Iy is integral of x squared dA. And if we want to integrate that to figure it out, well, look at dA. This differential element dA has a dx and a dy, which means a double integral, which means we want to try to avoid that if we can. So you can simplify this if you pick appropriately sized, appropriate thin strips to be the dA. So if you look here, this dA, we pick a horizontal strip. Okay, so this dA is this distance, which happens to be a minus x, right? This whole distance, and the thickness is dy. In this case, this dx, this dA is this thickness times this height, which is going to be y dx. Okay, so let's consider, for example, just real quick, a rectangular area. So here we have this rectangular area. Okay, ix is integral y squared dA. That's the definition of ix, right? Ix is integral y squared dA. Okay, so what do we know about this? Okay, so what is this dA? Well, it's this distance times this height. But this distance happens to be constant because it's a rectangle, right? We picked that on purpose. It's not an accident. And so it's a value of b, and the thickness is dy. So dA becomes b, as it says right here, dA becomes b dy. Well, if you integrate from 0 to h, right, you end up with 1/3 bh cubed. So ix, the ix of this little rectangle, so ix from this axis, right, is 1/3 base times height cubed. Okay, so now we're going to use that, and we're going to use that well. So let's come here. Let's talk about this strip. So I'm going to first ignore this one. Let's come back to this in a second. First, I want to talk about this one right here. So how do you do this? Well, you have this strip. So what do we know about the strip? It has the dA of this thing is what? It's the area is the height times width. The width is dx and the height is y. So diy is integral of x squared. So iy is integral of x squared dA. So diy is just x squared dA, right? And so dA is y dx. So is that all okay? Well, it is. And the reason we could get away with that is what? At this point here, at this point in the differential strip, it is a distance of x from the axis that we're concerned about. At this point, it is a distance of x from the axis that we're concerned about. We specifically picked a strip that maintains a constant value x away from the axis that we care about at any point in time. So that's how we can get away with going from a double integral to a single integral. Now let's look at this right here, the ix. So this is your answer. diy is that, so you can integrate through, and you have iy is integral of x squared y dx, or integral of x squared dA. But let's look at this. Dix. Is this point here a constant distance from, within this strip, is it all maintaining a constant distance from the x-axis? Well, it's definitely not. So you cannot just, you want to say, hey, well, diy is just x squared dA, so it's x squared y dx, so y is not dix. Y squared dA, so integral of y cubed dx. Well, it doesn't work that way because you cannot simplify a double integral to a single integral if it's not holding that thing constant. So instead, what are we going to do? We're going to say, hey, we learned something about rectangular areas. So this is a rectangular area, right? Well, what does this look like? Well, if you look at it, and if this dx is really small, this is just a rectangular area. And what do we know about rectangular areas? We know that the ix is 1/3 base times height cubed. Well, in this case, we're going to talk about the dix. So what does that mean? The ix of this differential strip. So the ix of this little differential strip, we're going to call dix, is 1/3 base times height cubed. Well, what is the base? In this case, the base is dx, so it's 1/3 dx, and the height is y. So dix is 1/3 y cubed dx. So again, 1/3 base times height cubed. So in one direction, you use this rectangular strip area, and in the other direction, you say, hey, you know what, I'm holding one thing constant, so I can use the dA defined by this, which is y dx. We'll do some examples of that to make that clear as well. Now, polar moment of inertia. So those are both the moments of inertia with respect to the x and the y-axis. Well, the polar moment of inertia is an important parameter. It has to do with problems involving torsion of cylinder shafts and rotations of slabs. Okay, and so how do you figure that out? Well, it's called J naught, J0, is integral of r squared dA, right? So that's nothing too exciting. But this can actually be related to the rectangular moments of inertia. Why is that? Well, what is J0? I'm sorry, what is r squared? R is x squared plus y squared, right? So J0 is r squared dA, which is integral of x squared plus y squared dA. Well, you can go through and you can multiply dA throughout each one, and then hopefully these look very familiar, right? Integral of x squared dA is iy, integral of y squared dA is ix. And so J naught is just the sum of the iy and ix, which is convenient way to find it. Okay, now we're going to talk about a concept called the radius of gyration, and specifically the radius of gyration of an area. Okay, so say you have your blob, right, your potato chip blob, and it has an area and it has a moment of inertia ix. So if you could somehow take that blob and concentrate it into a thin strip, boom, where you have the same area and it's at some distance from the x-axis, right? So the idea is that I have this blob and it has a certain moment of inertia about this x-axis. Well, if I could make a thin strip, and that thin strip has the same area and the same moment of inertia about the x-axis. The distance from the x-axis for that strip to be at in order for those things to occur is what we're going to call the radius of gyration. So Ix is k squared x a. So when you solve for kx, it's integral, or sorry, it's not integral, it's the square root of Ix over a. Okay, so that is the radius of gyration with respect to the x-axis. Now this is going to come as a shock to you, but we also do the same thing with respect to the y-axis. So it's the same idea, but now you're putting the thin strip at some distance from the y-axis, and Iy ends up being, ky ends up being the square root of Iy over a. And then lastly, the polar radius of gyration is the same idea. It ends up being square root of j naught over a. So those are the radius of gyration. So let's do some examples. Hopefully these will help clear things up. We're going to do examples 9.1 and 9.2.